All right, so we're going to look at one more way we can combine functions in this video. If you saw the last one about combining with operations. Now we're going to combine using a process we call composition. So I, again, have two functions here to use as examples. And I'll start by just giving the definition of composition. So we compose two functions, we use this symbol. So I'll write f composed with g. So it's not a little O, it's like a little circle, which I guess is also like an O. So I guess it is like a little O, but it's not the letter O, it's smaller than that. It almost looks like times, but it's an open circle instead of a closed circle. Instead of a dot, it's filled in. And we would say f composed with g of x, right? This is a new function. You can think of, this is one way to write the name of a new function using these symbols, right? Its definition is this, f of g of x. So what does that mean? Well, that means if we're given an input x, we put that in to the function g, g does what it does, and then gives its output to f, and then f takes that output, does what f does, and spits out a new output, right? If we think of our little function machines, we start with f, we put it into our function g, g spits out a new number, g of x, we put this into the function f, and then f spits out f of g of x. Right, it takes that number, right? So just notice this is a number, we get a new number spitting out, put that into f, f takes that new number and spits out another number. So let's do this for a couple of values. So let's take f of g of x of 2 for this function as I've given it. All right, so let's go ahead and compute, first of all, let's compute f of 2, 1 over 2 plus 1, or 1/3, and g of 2, 2 times 2 squared minus 1 gives me 7. So if we now do f composed with g of 2, this will give us f of g of 2, or this is the definition. That's f of g of 2. G of 2 we just said is 7, right? So now we have to compute f of 7. Let's come up here and compute f of 7. That's 1 over 7 plus 1, or 1/8. Okay, so f of g of 2, or f composed with g of 2, spits out the number 1/8, right? So again, we started with the number 2, we put it into g, g spit out the number 1/8, we put that into f, and then f spit out, g spit out the number 7. Sorry, I copied the wrong thing. G spit out the number 7. We put that into f, and then f spit out the number 1/8. Okay. Let's see something interesting about this. Let's look at, we can compose this in the other direction. G composed with f of x is going to be g of f of x. We're reversing the order. Now we're doing f first. We put in a number, we compute, we evaluate f at that number, we put that number into f, get an output, and then we take that number and put it into g. So let's do this for 2 again. This is g of f of 2. We computed f of 2 up above. I got 1/3. Now we do g of 1/3. G of 1/3 is 2 times 1/3 squared minus 1. So that's 2 ninths, right? 1/3 squared is 1/9 times 2 is 2 ninths minus 1 gives me negative 7 ninths, right? 2 ninths minus 9 ninths gives me negative 7 ninths. And that's my G composed with F of 2, right? Notice, right, despite the fact that the composition symbol looks a lot like the multiplication symbol, it's not at all the same process. In particular here, notice it doesn't commute, right? If you reverse the order of multiplication, nothing changes. 2 times 3 is the same as 3 times 2. But here, changing the order changes it dramatically, right? These are not the same result at all. And that's typically going to be true. We can construct some examples where switching doesn't change anything, but in most cases it will. Okay, so there's our composition of functions. Let's look at another couple things of interest. Or first, let's do this. Let's look at, we can write f of g of x in another way. So we can, if we want to get an algebraic expression for this, just like we did with operations, sometimes we evaluate it at the 2 values and then multiplied or divide, added, subtracted, whatever we were doing. But we also use the algebraic manipulation to just come up with a new expression for those functions when we combine them. We can do the same thing here. F of g of x means put g of x into f. So here I have g of x, 2x squared minus 1. And then we take 2x squared minus 1 and put it into f. So I have 1 over 2x squared minus 1. We add 1 to that, and we get 1 over 2x squared. Right? And notice if we evaluated this at the number 2, we would again end up with the result 1/8 that we got up here doing it the other way. Let's look at the reverse. G composed with f of x, g of f of x, which is g of 1 over x plus 1, which is 2 times 1 over x plus 1 squared minus 1. There's not a whole lot of great ways to write this. I'm not going to do much to this. So we could write this as 2 over x plus 1 squared minus 1. That's a good enough way for now to write this. All right, and again, we can see that these are not the same expression, right? These are 2 different functions here, as we expect. Reversing them changes the result, right? And this is not typical for us, right? Typically, you know, things like we're used to things like multiplication where we can reverse the order. Another thing to note is about domains. Notice the domain of f, let's write the domain after it, is x not equal to -1, right? We get a 0 in the denominator. Here we've got a parabola. We can put any real number into x there, square it, multiply by 2, and subtract 1. There, the domain is all real numbers. Let's look at f composed with g of x, this function right here. All right. So the domain of f composed with g of x, which we just wrote as 1 over 2x squared, well, it's pretty easy to see in this expression that we should have x not equal to 0, right? How does that relate to the domains of those 2 original functions, right? It doesn't really seem to have any connection there. But let's notice something. If we look at the domain of f, which was x not equal to 1. And think about what our composition does. We put a value into the function g, we spit out a value of g spits out a value for us, and then we put that function, that number, into f. So what we need is to make sure that the thing that g doesn't spit out doesn't cause f problems, right? G can take any number, its domain is all real numbers, but we need to make sure that g of x is not equal to 1, because we're going to get whatever g of x does, we're going to give it to f. And if g of x gives us a 1, then, sorry, negative 1. I wrote the wrong thing here. Sorry, negative 1. If g of x gives us a negative 1, that causes problems for f. So when is g of x equal to negative 1? That's when 2x squared minus 1 is equal to negative 1. Sorry, I just lost my train of thought for a second there. If I add x 1 to both sides, I get 2x squared is equal to 0. And you can see this is true when x is equal to 0. So in order for g of x to not equal 1, we need x to not equal 0, which is exactly what showed up when we wrote this expression here, right? So that's how you have to think about domains. You have to start with, first of all, the inner function, g, in this case, g of x. We have to make sure that whatever x we give g knows what to do with it, right? In this case, we didn't have a problem, but that's not always going to be the case. Your inner function could have some restrictions on the domain. But then you also have to think, okay, then what about what comes out of g? What comes out of the first function? Can the next function handle it, right? And you have to think through both of those steps. One other thing we should think about, let's do a new example. We'll do a little bit of a maybe simpler example to get at one other point. Let's start with two new functions. Let's call f of x 1 over x and g of x 1 over x plus 1. Let's look at g composed with x, with f. G composed with f of x is g of f of x. Let's do this a little bit differently. Instead of putting an expression for f into here, let's take f and put it into g. In other words, I can write this as f of x plus 1 in the denominator, right? I'm doing g's thing, but instead of x, I have an f of x in there. And now I can replace f of x with 1 over x plus 1. So here's my function g composed with f of x, right? Let's do a little bit of algebra to this thing. So this I can rewrite as 1 over x plus x over x, or 1 over 1 plus x over x, right? And then 1 over something, we simply take the reciprocal. And so now I have this expression for g composed with f of x as x over 1 plus x. Right? Okay, there we got a nice algebraic expression. Now let's do g composed with f of 0, and I have 0 over 1 plus 0, or 0 over 1, which is equal to 0. And everything seems fine, but everything's not fine, right? So again, we had an example like this in the previous video about combining functions. When we have division, we can sometimes do some algebraic manipulations that hide a problem from us. And our problem here is that this function doesn't actually work at 0. Let's see why. The definition of g composed with f of x is take a number, give it to f, let f do its thing, and then give the new number, the result of f, to g. Well, when we do g composed with f of 0, we get g of f of 0. However, look at f. F of 0 is not defined. And so there is no g of f of 0. There's no g composed with f of 0, right? If we go back to that little map, we're taking x, we're putting it into f, taking what f does, putting it into g. The problem is nothing ever comes out of f. We get broken down in the first step, right? Because f of 0 is not defined. 1 over 0 is not a defined number. What happened was in this step right here, right, 1 over a number is the reciprocal of that number, right? That's true, except when that number, well, is not defined, because if you look at the number when x is 0, this isn't a number. 1 plus 0 over 0 is not a number, so a non-number doesn't have a reciprocal, right? So this was a nonsense step in the case that x was equal to 0, which is exactly the case we ended up being interested in, right? One other way to think about composition of functions that might help illustrate this point. Remember, we can think of functions as, sorry, let me say one more thing. So back to the domain problem we talked about at the end of this page, right? We have to start in the domain of f, and that was another problem, right? It's a little more obvious here. 0 is just not in the domain of f. It doesn't matter about g even at that point. We have to start with numbers in the domain of f before we can even think about what happens with g, okay? One other way to think about this, this is a way I like to conceptualize functions sometimes, is as a set of instructions, right? So f is the function that take reciprocal, right? G of x is the function that add, so let's say of input, add 1 to the input, and then take reciprocal of result. When we do g of f of x, what it means to do is first do the instructions for f. So take the reciprocal of input, then do the instructions for g, right? Take the result of f and put them in as the new input to g, take reciprocal of result, right? A problem, again, is that at this first step, the input 0 doesn't have a reciprocal. And so in this new set of instructions, we have a problem in the very first step. This is another good way to think about composition. You take the instructions for the inner function, right? I know the ordering is a little bit weird because we think, but the reason is we think of the inputs kind of traveling this way through our functions, right? When we do f of x, x goes into f. So here, x goes through f, then into g. We do f first. So when you do composition, you can take that inner function and do all of its instructions, and then immediately start the next set of instructions, right? I always think about it as if you have a function that tells you whose instructions are to how to mix a cake and then how to bake a cake, if you compose them, if you bake of mix of a cake or something like that, you'll start with the instructions for mixing it and then you'll bake it. If you flip those, you get something very odd because you've cooked all the ingredients before you mix them together, which also illustrates maybe a thought about why we can't reverse this process. Okay, that's it for this one. Thanks, everybody. I will see you next time.